Chem 107 students, welcome to Chapter 2. Chapter 2 is on ozone. Make sure you have printed out your periodic table and shapes table. For this chapter especially, we'll be using it. Your periodic table looks like this, and your shapes table looks like this. I put them back to back in a page protector to keep them safe. So you should have these two items printed out for this chapter. Before we proceed, go ahead and get those. All right, now we talked a little bit about ozone in chapter 1, but we talked about ozone as a pollutant down here where we have cars driving in sunny places like Mexico City and Phoenix. So ozone down here is bad because it's a pollutant. So I'm talking about down in the troposphere where we live. So if we're looking at the layers of our atmosphere, the lowest down close to us is the troposphere, where we have smog and other pollutants, including ozone. Then as we keep going miles up higher, we reach the stratosphere. And then miles up in the stratosphere, we have a protective ozone layer. Now the ozone way up there is actually good for us. That's the good ozone. And that's what I mean when I say the ozone layer. I'm talking about the protective ozone layer at the top of the stratosphere. So not the bad ozone down here that's the pollution. Why is the ozone layer way up high in the stratosphere good? Well, it's a layer of our atmosphere where we have a lot of O3 molecules. Well, not a whole lot, but there's some. And it protects us from getting skin cancer. We get skin cancer from ultraviolet UV radiation. So ozone up high in the stratosphere is very good because it protects us from getting skin cancer. Again, the bad ozone is the one down in the troposphere down here with us that is a pollutant. So this chapter, we're going to talk about the good ozone up in the ozone layer, up high at the top of the stratosphere. So the ozone layer covers our complete planet. However, we have determined there is a hole in our ozone layer. Now, we've known about the ozone layer since 1913. The concentration of the ozone layer is about 10 ppm. Remember what ppm means? Parts per million. Yeah. Now, even though that's a small concentration, it's enough to absorb about 98% of the ultraviolet radiation in the 280 to 320 nanometer wavelengths. And that's the kind that causes the skin cancer. However, we have discovered in the 1980s, that there's a big hole above Antarctica. Now, Antarctica is North or South Pole? South Pole, right? It's the South Pole. So Antarctica has a hole in its ozone layer, and that's what is depicted in the purple and blue. That's a lack of ozone. Green means there is ozone. Now, not a lot of people live there, that's true, but should we be concerned about this hole? What if it were to spread to where we live? Our skin cancer would skyrocket. So we discovered this in the 1980s, and in this chapter, we're going to learn what we did about it. So NASA has an Earth observing system. It's a bunch of satellites up in our atmosphere. NASA's EOS started in 2004, the Earth observing system, and it monitors things like climate change and ozone. So it also monitors the air quality that we talked about in chapter 1. So this could be a good project for you. If you wanted to do your project on NASA's Earth observing system, you could learn all about it. So that would be a good project for you to do. All right, let's talk a little science now. I mentioned UV waves having a wavelength. What did I mean by that? Well, if you look at the pictures, I have two waves, right? Waves go up and down like this. So the top wave has a longer wavelength. That's the distance from peak to peak of a wave. So it has a longer wavelength. Longer wavelengths have lower energies. They also have lower frequencies. Frequency is how many peaks pass by in a given second. So a long wavelength has a lower frequency. It's like it's beat, like a heartbeat. So a long wave is like beep, beep, beep. Now the bottom wave has a much shorter wavelength, which means the energy is higher and the frequency is higher. Listen to its beat. Beep, 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 beep. See, it's a lot more fast. It has a higher frequency. So higher frequency, there's more beeps per second. Its beat is faster, so it has a higher frequency. So longer wavelengths are low energy and low frequency. Short wavelengths have higher energy and high frequency. All right, so let's see if you understood that. As the wavelength increases, getting bigger, energy does what? Go up or down? As the wavelength increases, energy goes down, right? Decreases. All right, second one. As frequency decreases, wavelength does what? So that's its beat. As the beat slows down, what's happening to the wavelength? It's getting longer, right? It's getting longer. It increases. As energy increases, frequency does what? So higher energy, higher frequency. The frequency increases as well. Yes. Very good job. Hopefully you got those right. We need to understand our relationships between these terms when talking about waves. Now this picture is all the waves together. Starting at that end on the far side, gamma rays. Those are short waves that have high energy and high frequency. In fact, if you're exposed to gamma rays, it can cause cancer. So we don't want to do that. So gamma rays are first. Next up, X-rays, also high energy, high frequency, not as high as gamma, but still pretty high. And in fact, if you're exposed to a whole bunch of X-rays, it does increase your chance of cancer a little bit. So that's why you don't routinely get X-rays at a physical. You only get an X-ray if you need it. Next to X-rays is the ultraviolet. Again, ultraviolet rays have some energy, high frequency, enough to cause skin cancer. Ultraviolet. Then we get to visible. You can see the visible is that little bitty section of the rainbow in there. At this point, we're getting safe. So visible is what our eyes detect, the visible colors from red to purple. Next to visible is infrared. That's heat waves, IR, heat waves. And then we're really getting longer and lower energy now. Microwaves, longer, lower energy, lower frequency. And then radio waves can be, a meter long, a football field long. So radio waves are like this long. They're long. They have really low energy, really low frequency, and don't hurt us at all. So you need to remember these in order: gamma, X-ray, UV, visible, IR, microwave, radio. Remember these in order. All right, questions. Which waves were the longest? Radio, right? Which waves were the shortest? Gamma. Which waves cause heat? Infrared, IR. Which waves can we see? Visible. Now here's a trick question. Which waves travel the fastest? You probably said gamma. Let's have a little race. Look at me real quick. We're going to have a high frequency and a low frequency wave going across the screen. Ready, go. They're traveling at the same speed, aren't they? They got here at the same time. Now, one of them is going up and down faster. That's its frequency and energy. But the forward progress was the same. So they travel at the same speed. So that's a trick question. All waves travel at the same speed. What speed? What's the fastest speed we go? Light speed, right? All waves travel at light speed, all of them. How many waves are hitting you right now? Thousands. We got light, we got heat, we got radio, we've got cell phones. They're all hitting us. Are you melting? No. So most of our waves are not dangerous. All right, longest waves, radio. Shortest waves, gamma. Heat, infrared. C, visible. Travel fastest, all light travels at light speed. How many waves are hitting you? Thousands, millions. Are you melting? No, you're okay. And I think we'll end our first video there. So see you in the second video for the second chapter. Thanks, guys.